Applications built in the cloud are often serving requests from all around the world. A user in Hong Kong could have written to a database entry at the moment just before a user in San Francisco and a user in Germany simultaneously try to read from that database. If the user in San Francisco is allowed to see a different database entry than the user in Germany, that database is not strongly consistent. Strongly consistent databases work such that two users who read the same entry at the same time will receive the same result. Weakly consistent or eventually consistent databases are suitable for applications where transaction ordering is not important. For example, photo sharing apps and e-commerce shopping carts. Bank accounts, on the other hand, often need to be strongly consistent. CockroachDB is a scalable, survivable, strongly consistent database. Alex Robinson is an engineer at Cockroach Labs, and he joins the show to explain the data model for CockroachDB and how it maintains strong consistency. Spring is a season of growth and change. Have you been thinking you'd be happier at a new job? If you're dreaming about a new job and have been waiting for the right time to make a move, go to hired.com/sedaily today. Hired makes finding work enjoyable. Hired uses an algorithmic job matching tool in combination with a talent advocate who will walk you through the process of finding a better job. Maybe you want more flexible hours, or more money, or remote work. Maybe you want to work at Zillow, or Squarespace, or Postmates, or some of the other top technology companies that are desperately looking for engineers on Hired. You and your skills are in high demand. You listen to a software engineering podcast in your spare time, so you're clearly passionate about technology. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $600 signing bonus from Hired when you find that great job that gives you the respect and the salary that you deserve as a talented engineer. I love Hired because it puts you in charge. Go to hired.com/sedaily, and thanks to Hired for being a continued long-running sponsor of Software Engineering Daily. Alex Robinson is an engineer at Cockroach Labs. Alex, welcome to Software Engineering Daily.
Thanks, Jeff.
We previously did a show about CockroachDB, and today we're going to be talking about it in more detail. So I want to talk about cloud-native databases more broadly first. So we're in this era where people are talking about cloud-native, and people have different definitions of what that actually means. I think those different definitions are directionally similar, but I'd love to start off by getting your definition of that term, cloud native.
Yeah, so you're right that cloud native means different things to different people, but yeah, it's usually along the same lines. The general gist of it is that it's a system that runs well in a modern cloud environment, and a modern cloud environment is one in which processes often aren't around for a long time, and you don't really trust the hardware that you're running on. When AWS was new, you couldn't rely on a VM to be up and running for months at a time or years at a time like you can with your own server in a data center. And so this concept of cloud native came around as people started building their systems to run well in infrastructure where hardware isn't very reliable. Mm-hmm. So a cloud native system has to be something that can handle failures very smoothly, ideally without a lot of operator intervention. And that means that the system has to have some way of healing itself and recovering as nodes fail, or as disks fail, or as network links fail, and nodes can't talk to each other anymore. So this kind of cloud native system has to handle failures, be very automatable, because it's usually run in these increasingly complex environments where having operators manually do everything is impractical.
Right.
And finally, because you have to handle failures, the system has to be distributed in some way. Any process that can only run on a single machine at a time is almost by definition not cloud native, because any sort of failure is going to take it offline completely.
Most of the shows we've done about cloud native, whatever that means, we're often touching on these runtime systems like Kubernetes. Maybe I'm misappropriating that term runtime system. I just actually kind of made it up on the fly, but we're typically talking about containers, and these containers are things that are not very durable, or you basically have the expectation that this container can vaporize at any instant. And with databases, it's a little bit different. You're not exactly making the same assumptions. Help us understand, like, what is different about databases in a cloud native environment versus databases pre-cloud native. And I guess separate question, I don't mean to throw two questions at you at once, but when we're talking about the cloud native runtime, like a Kubernetes container in a Kubernetes environment or a Mesos environment versus whatever the system of runtime or system of operation that a database is running on, what's different about these two ways of managing state or managing user sessions or whatever?
So I'll start with the first question. And I think it's important to note that running something in a container doesn't have to be any different from running it directly on a host. The difference usually comes in how the tools that you're using treat those containers. Because if you're running a process, say a database directly on a machine, it's running as a process, and it'll usually keep running until you either kill it or until the machine fails. And the same thing is true if you decide I'm going to run that process in a container on that host instead. Until you or a tool does something to that container or to that host, that process is going to keep running inside the container exactly the same as if it was running directly on the host. So there's nothing inherently different about running a process in a container. Where the difference really comes in is that the tools that people use to manage containers are often a little more eager about killing them, moving them around, and things like that. So the difference between running a database in a container in an orchestration system versus running it directly on a host is that there are all these disruptions created by the tooling. So maybe you're trying to upgrade all your machines, or the version of Kubernetes running on all your machines, and you have to take the process down in order to do that. So that's introducing some downtime that wouldn't be there if you were running directly on the host. But the only real difference is that your process has to handle a few more disruptions. So if you're running a distributed process that can handle failures, this comes almost for free. So if you have 3 replicas of your data, for example, in the case of Cockroach, and Kubernetes decides to take one of them down for some maintenance, then the other 2 can keep serving all your traffic just fine. And when the other one comes back up, it'll just rejoin the cluster and start operating as normal again. So that's where this fault tolerance and automatability becomes really important in these environments. And so a database that wasn't designed to have multiple active replicas at once, so that might have a single active at a given time, is a bit tougher to operate in this environment because you have to have a process in place to transfer which replica is active at any given time when these maintenance events are happening.
When I first was learning computer science and programming, people were explaining disk versus in-memory to me, and they would often say, yeah, when you write to disk, that means that if your computer dies or it shuts down or whatever, that information is going to stick around. Even though your computer shut down, it ran out of power, whatever, you boot it back up, it still got whatever was on disk. And in-memory means this is something where if you shut the computer down, it loses the in-memory things. I think even then, that was an oversimplification of reality, and today that would be even further from the truth. But we still use these terms like on disk or saving to disk. We use these, term like durability. And I'll be frank with you, I don't really know what these terms mean anymore. Is there a simple explanation to this, or is this just like a simplicity that is an opaque layer over the reality, which is like really complex layers of caching and distributed systems and stuff?
Well, it's complex, not just in your head. It is a complex concept, in reality as well. There are different layers of durability. But what you might think of as an in-memory system, so there are databases out there on the market that are in-memory databases, but that still persist everything to disk so that they can recover. And so how those systems work is that they expect to be able to do everything out of memory. The whole working set of data has to fit in memory, but they are regularly logging all new writes to disk so that they can recover if something bad happens and they have to restart for some reason. So the data is durable, but the system is still an in-memory system. Whereas you could also have a database that isn't an in-memory database that does require disk to store all of its data because it can't all fit in memory, that are not necessarily durable because they don't flush their records to disk often. So there are systems out there that when you do a write, they'll acknowledge that write to you before that data is safely on disk. And if they then failed, your data would be gone even though you were told that it was written to disk. And then there are even further levels of this where a database can choose whether or not to fully sync that record to disk before acknowledging it. And certain types of hardware failures will maintain that data, even if you didn't sync it, but other types of hardware failures won't. So complete power failures might lose it, whereas rebooting the machine won't. And so there are a lot of different levels of durability. Durability also comes into question when you talk about a system that doesn't offer true consistency, because you could write write some value A to one of the nodes and write some value B to one of the other nodes, and one of them will clobber the other because you wrote them to the same key. And so both those writes will succeed, but the first one might not be durable because the other one clobbered it in a consistency race. So there are all sorts of ways to define durability and think about durability depending on what you're building and what you care about.
Okay, great. Thank you. That's a great disambiguation. I want to continue to talk a little bit of history and set some context for people who are unfamiliar with this space. We definitely have a hangover of the past where we have an association between like the database that you choose and this idea of vendor lock-in. So there are a number of providers who in the past, they looked at the idea of a database as an opportunity to lock in a enterprise customer. The enterprise puts all their data into this database, and porting that data to something else or porting it to something else that the organization can manage themselves without using proprietary software is difficult or impossible. And then since that era of time, I don't know if you're talking about I guess that's 90s, like mid 90s, early 90s / early 2000s, we've kind of moved a little bit away from that, where there's it's a competitive edge for a database to provide less vendor lock-in. What's the state of kind of vendor lock-in in the marketplace, and how does that manifest in engineering features?
Lock-in is a really tough thing to avoid. Everyone is worried about it these days, much more so than they probably used to be. But lock-in is almost
overly
natural.
Worried. Sorry to interrupt, but maybe overly worried, right?
Perhaps, yeah. I mean, because lock-in is almost a natural effect of adding more advanced features to a system. If you add some cool new feature to your database that other databases out there don't support, and your users come to rely on that, that's a form of lock-in, even though it's something that's absolutely a net win for those customers. Mm-hmm. It's a feature that they rely on that makes them building their own business easier, but it makes it harder for them to move off your system because your competitors don't offer it. So it's tough to get rid of lock-in completely, and trying to do so would probably be a fool's errand. But there's definitely broader levels of compatibility that can be strived for. So with CockroachDB as an example, we are using the PostgreSQL wire protocol and are trying to mimic as much of their syntax and as much of their features as possible, so that it's very easy for someone who's using Postgres to just swap out their backend and put CockroachDB in its place. Mm-hmm. And it's a lot of work to do so because PostgreSQL has been building up for decades, adding more and more features, more language quirks, and more things that needed to be supported. And SQL is a standard, it's the standard query language for most databases, but it differs between all SQL databases. There are queries that will run in MySQL that won't run in Postgres, or that won't run in Oracle, and vice versa. For any pair of databases that you can imagine, you can come up with incompatibilities. And so, SQL kind of mirrors this idea of lock-in pretty well, in that it's at a place where lock-in is small. It's easy to change databases in that only some of your queries will have to be rewritten and only partially. But true compatibility and complete lack of lock-in is just not possible in the space that we're in. Mm-hmm.
Grammatech Code Sonar helps development teams improve code quality with static analysis. It helps flag issues early in the development process, allowing developers to release better code faster. Code Sonar can easily be integrated into any development process. Code Sonar performs advanced static analysis of C, C++, Java, and even raw binary code. Code Sonar performs unique data flow and symbolic execution analysis to aggressively scan for problems in your code. Just like battleships use sonar to detect objects deep underwater, engineers use Code Sonar to detect subtle problems deep within their code. Go to go.grammatech.com/sedaily to get your free 30-day trial exclusively for Software Engineering Daily listeners. Code Sonar analyzes your code, and it delivers a detailed report. The The CodeSonar user interface provides all the information that you need to quickly understand the reports, follow cross-functional paths, understand cross-references, quickly navigate between files, and visualize large pieces of your code. Go to go.grammatech.com/sedaily to get your 30-day free trial and unleash the power of advanced static analysis. Thanks to Grammatech for being a sponsor of Software Engineering Daily. In, I think it was like 2005, 2006, somewhere around that time, NoSQL started becoming really popular, and there were a number of reasons why. I think two biggest reasons that come to mind is, one, JavaScript was getting really popular, so people were looking at JSON, and they were like, well, it'd be cool to have a database that looks like JSON. Okay, cool. We get this document database, MongoDB. It's NoSQL. And then maybe the other reason is it's schemaless, so you can easily add fields to some subset of your entries in the database, and it doesn't really complain as much. And that was useful because you had all these startups that were getting started because of the cloud, the popularity of the cloud. So there was this huge growth in startups, and so you had these startups that were moving fast and they wanted to change their schema, and so that made NoSQL much more appealing. What were the upsides and the downsides of this boom in cloud native usage of NoSQL? Just give me your perspective on, I guess it's been 10 years roughly, kind of since these NoSQL databases started becoming really popular. Give me your perspective on that history.
I mean, I think it's kind of interesting because these systems were first created in order to reach greater scale and greater availability. These systems were coming out of Google and Amazon and Facebook, who were building them not because they wanted a schemaless database, but they were building these systems, Bigtable or Cassandra or Dynamo. They were building these because of the greater scale and availability that they could gain by getting rid of the SQL interface and moving to something simpler. But then it is very interesting that these systems gained broader adoption in the marketplace for the opposite reason, for the reason that the lack of a schema made it easier to move fast and change your system more frequently. I think there's a lot of value to both sides of that coin. When you are small and when you're a new system and you're changing frequently, if your database makes it hard to change your schema, you're going to have a rough time, and you're probably going to want to use a different database. And traditionally, SQL databases have not made it very easy to change your schema while you're still serving traffic. Mm-hmm. So I think there's real value to both sides of this coin of whether you have a schema or don't have a schema. But some of the pain can be lessened if your database supports very painless schema changes that can be done in the background without stopping any user traffic. It makes it much, much easier for a startup to deal with working with a SQL database that requires a schema. Mm-hmm. This is kind of a tangent, but I think there's an interesting parallel here to the story of containers. Containers were the technology behind containers in Linux were built out so that companies like Google could get better resource utilization and they could isolate processes.
Right.
But then the reason they were adopted in the market was due to their packaging features that Docker added in. And so it's this one idea of containers that that was created for one reason but gained popularity in the marketplace for another.
What are the features that the NoSQL databases kind of don't solve as well? What are they lacking? And if you're a modern startup, you've gotten going, you've got this this NoSQL database that's just giant that you started with a NoSQL database because you had no users and you were moving fast, and then over time you're like, oh, holy smokes, we're actually now using a NoSQL database at scale. What penalties are you going to pay for being all NoSQL?
Well, the biggest penalty is just the lack of trust that you can have in your database. You can't always be confident that what's there is correct or that what's there is in sync, because almost all NoSQL systems sacrifice consistency in order to provide that greater scale and availability. And so if your system is running on a NoSQL database, you probably have a lot of workarounds in your code in order to deal with your data sometimes being out of date. And that's by far the biggest pain that you're going to have to deal with. You might also be upset by the lack of indexes. So you're going to have to manually maintain your own indexes in some cases, depending on what system you're using and what kind of indexes you want. And whenever you start manually maintaining your own indexes to allow for faster reads, you're probably going to end up with some incorrectness in those indexes as well. And so it's really just this lack of consistency and lack of correctness that's going to be by far the biggest problem for large NoSQL deployments.
Okay, perfect. This is where I wanted the conversation to go. When do we need consistency or correctness or whatever term you want to use to describe that? Why do we need consistency? And reiterate why we might lose that if we're entirely using NoSQL databases.
There's nothing inherent about NoSQL systems that require them to be inconsistent. CockroachDB internally has a NoSQL database, inside of it that is consistent, but most out there on the market are inconsistent. So we'll talk about them as if they are. And the problem with inconsistency is that it puts more responsibility on the developer who's using that database to be able to use that data in any given way. Because whenever the developer wants to use data from the database, they have to think, is it okay if this data is slightly out of date? Or is it okay if my first write succeeds, but then my second write never happens because the process crashes? Which is especially important in a cloud-native environment where a process could be taken down anytime. So the developer has to think about a lot more when operating against a NoSQL system, even if it's always okay to lose a write or to read old data or for copies of the data to be out of sync. Even if that's always okay, there's still a large cognitive overhead on the developers of the system having to think about that every time they use the database for anything.
When I talked to Ben Darnell, who works at CockroachDB, one of the co-founders, it sounds like he didn't really like this term eventual consistency, which is a term I've talked to different people about on this show. That term eventual consistency, is there anything wrong with that? How do you define that term eventual consistency?
Well, I mean, it's defined almost exactly as it sounds. It means if you do a bunch of writes to your database and then stop using it, the database will eventually be consistent. So all the copies of data will eventually be caught up and agree with each other. But because it's eventual, that means at any given point in time, it might not be consistent. So it's really just saying there are no guarantees. You cannot guarantee your data is going to be in any consistent or correct state at any given time. It just will eventually be consistent. And so it's really not offering you a feature so much as explaining the lack of a feature.
Yes, indeed. And why are the bugs that we might have as a result of eventual consistency, why is it so hard to think through how those bugs might manifest?
Well, concurrency is inherently tough for people to think about and to deal with. When you're writing a program locally, you can sort of trust that you know what all your data is going to be. If you do a write into some memory location and then another, later on you want to read from that memory location, it's easy to reason about what's happening in your program. It's tough to reason about this kind of delayed data store where what you're reading might not be correct. And so it's just not something, it's not a way of thinking that comes very naturally to people. And it very often leads to bugs in production.
Well, I mean, I think it's basically it's like dining philosophers. It's like any race condition that you can imagine in computer science. Basically, like if you make a big series of writes and they end up writing to, let's say those writes happen at the same time in different parts of the world, and they end up writing to different replicas of the same database, it's going to take some period of time for the conflict in so how are we going to sort out how these writes are linearized or serialized or whatever term you want to do? If you need to time order some writes that essentially happened at the same time around the world, and you need to make some global resolution on what order those writes occurred in, those different database nodes are going to need to resolve the different writes that occurred. And in the meantime, if other people are reading from that database, you may not have guarantees about the consistency. Although I guess that's not a great example because there's essentially no objective thing you could say that this one occurred first if they all occurred at exactly the same Unix timestamp. But even if they were a millisecond off and these occurred in different places in the world, you would have some period of time where there would be some inconsistency, I guess.
You can kind of think about it as trying to write a concurrent program that doesn't have locks or doesn't have atomic memory access.
Exactly. That's exactly it. So, okay, that said, if I want to build a consistent database, what sacrifices do I have to make? What am I going to have to do?
Well, the biggest sacrifice you're going to have to make, if it's a well-built system, is latency. So any consistent system that has multiple copies of a piece of data is going to have to talk to it more than one of those copies. If there are 3 copies of a piece of data, at least 2 of them have to agree on something to guarantee consistency. And that means that in order to commit anything in the system, you're going to have to pay for a network round trip between it, at least 2 of those copies of the data. Whereas a system that isn't worried about consistency could commit a write before it's talked to any other nodes. So that's a fundamental sacrifice that you have to make in order to provide consistency in a distributed system, is that there's more communication cost that you have to wait for when making any sort of write. Mm-hmm. But beyond that, there's not much inherent that you have to give up. The system might be more complex to implement, but it doesn't necessarily have to have worse throughput. It doesn't necessarily have to be slower in any way other than network latency. It doesn't have to have lower scale or anything like that. The only thing you really have to give up is the network communication cost.
And I think, it's not like a system of trade-offs that adds up to something bad. It's just a trade-off, and that's why there's you're working on CockroachDB, which is a database that makes a set of trade-offs that give you strongly consistent SQL. And I want to dive into that to give people an understanding of why there are so many different databases in the world. I think this is just a case in point of every different database is making some different trade-offs. So what are some of the key differences that CockroachDB does implementation-wise to provide that strong consistency?
So as I mentioned, we have to store multiple replicas of each piece of data in order to provide availability in the case of failures. That's almost a requirement in order to be available in a cloud-native environment. So we have multiple copies, and in order to be consistent, we have to keep those copies in sync. They have to reach some sort of agreement on every write to the system, whether or not the write is accepted. And so for every copy of data, or for every write to a given piece of data, we have to reach consensus using what's called a consensus algorithm. When we use the Raft consensus algorithm, it's fairly similar to the Paxos algorithm. And so every write in the system has to go through this consensus process where the 3 copies of data are effectively voting on whether or not to accept the write. So every write has to do this, which is in stark contrast to what a NoSQL system might do to accept a write. So that's the biggest difference. But once we have that low-level foundation that allows us to do consistent writes to a single consensus group, we build on top of that a whole network of a large number of thousands or tens of thousands of these consensus groups. So we split our data up into a large number of ranges. So we break the data up into chunks, and each chunk forms its own consensus group that makes agreement on any given write. Mm-hmm. So if you're writing a single key, that will go to a single one of these groups, and that group will agree on whether or not to write that key. If you're writing multiple keys in a single transaction, then we have to coordinate those groups at a higher level to make sure that all those writes either atomically do or don't happen. So there's a lot of code and logic on top of this consensus protocol in order to accommodate a full SQL system.
Okay. I want to go from the ground up and talk through the architecture of CockroachDB. So we'll get at a certain point to different discussions of that consensus model that you discussed. But let's just start at the lowest level of CockroachDB. If I'm storing some database entries, what's going on at the lowest level?
Well, the very lowest level of any database is writing the actual bytes to disk. And so at the very lowest level of Cockroach, we're using something called RocksDB. RocksDB is what's known as an embeddable key value store. Embeddable meaning that it's almost like a library that you link into your process. And it's this embeddable key value store that's been open sourced by Facebook and was originally open sourced by Google called LevelDB. So Google wrote LevelDB, which is effectively how they store their bytes on disk for their systems of record in their databases. And they open sourced this. Facebook improved it to work better on modern disks like SSDs. And we are writing our bytes to disk using RocksDB. So we don't actually write our own code for dealing with disks. When we want to write a given key value pair to disk, we pass it down into RocksDB and ask it to persist it for us.
Okay, so now we understand the database entries at the lowest level. Let's start to talk about the replication model. If I have this entry that's written in RocksDB on disk, what's going on replication-wise? Like if a write occurs and it's written at the lowest level of disk, where else is it written? When is it written? Why is it written?
So between those points, actually, there's a layer of version control, multi-version concurrency control, where we keep multiple copies of each key on disk. So I can go into that if you would like, or we can move up the stack. What would you like?
Interesting. Let's have our cake and eat it too. Elaborate on the lowest level, and then we'll move up.
Right. So while we write individual key value pairs to disk, for any given logical key in this key space, we maintain multiple copies of it in what's known as multi-version concurrency control. So if you write to key A at time 1, we'll write that copy to disk. And if you write to key A at time 10, we'll write that copy separately so that we still have the key at time 1. And this is important for things like supporting reads that are in the past. So it enables transactions to continue operating concurrently, even though they might be reading and writing to the same key. The read can work on the value that's in the past if the timestamps work out that way. And this really helps a lot with high concurrency workloads. To move up the stack to the replication, when a key is being written to disk on one node, any write that we do gets passed through Raft. So in order to be written, we have to propose a command to Raft. And this Raft consensus algorithm internally will work out on each machine whether or not it needs to be written to disk. So one of those nodes will be the leader of the Raft group. That leader will write it to disk locally, then pass on the key value pair to the followers of the Raft group. The followers will then write that key to disk and respond to the leader saying, I wrote it. And once a majority of the nodes have written it to disk, the leader will consider it committed and then do what's known as applying that write to disk. So we're really storing this data twice. Once in Raft's internal log, where it keeps track of what it's been working on, and then once in the actual data store, once Raft has decided that the write has been committed.
Okay, so I think if I followed you correctly, we're still just talking about a single box, and now we can get to distribution, which is on top of the replication. Once you have some replication, you want to distribute it. Is that correct?
Yeah, so this Raft process is
I guess
dealing
Raft,
with
right.
machines.
Raft is the distribution, right? Of course, yeah. Okay, right. Okay, so let's talk about that a little bit more. I guess explain the distribution layer in more detail.
So, as I mentioned, each command that we propose goes through this process where, say a user wants to write key A. That goes to the leader node for the Raft group, and that leader node packages it up in what's known as a Raft command. It writes that Raft command to its Raft log, and this log is just this sequential ordered set of commands that all the Raft nodes have the exact same Raft log, or eventually come to the exact same Raft log. Every command is in the same order, in the same position in the log. And that's what they use to come to agreement. So for a new command, the Raft leader will write the new command to its log, send it to the followers, and if everything's going well, they will write that same command to their logs and tell the leader that they did. And once Raft knows that command has been committed to a majority of the nodes, then each one of those replicas can take that command out of its Raft log and apply the command to the actual database. So the Raft log is stored separately on disk from the actual data in the user's database. And so it's a separate step to actually say, now that the command is committed, we're going to apply that state to the real system so that reads will see it and other writes can write over
it. Your application sits on layers of dynamic infrastructure and supporting services. Datadog brings you visibility into every part of your infrastructure, plus APM for monitoring your application's performance. Dashboarding, collaboration tools, and alerts let you develop your own workflow for observability and incident response. Datadog integrates seamlessly with all of your apps and systems, from Slack to Amazon Web Services, so you can get visibility in minutes. Go to softwareengineeringdaily.com/Datadog to get started with Datadog and get a free t-shirt. With full observability, distributed tracing, and customizable visualizations, Datadog is loved and trusted by thousands of enterprises, including Salesforce, PagerDuty, and Zendesk. If you have not tried Datadog at your company or on your side project, go to softwareengineeringdaily.com/Datadog to get a free t-shirt and support Software Engineering Daily. Our deepest thanks to Datadog for being a continued sponsor of Software Engineering Daily. Okay, so at a fundamental level, we're talking about an event log of changes that the different nodes that are storing a certain piece of data have to come to an agreement on. So are we talking about different replication logs for different nodes that are concerned with different types of entries, or is there some global replication log, global event log that every node is concerned with?
So every node has its own Raft log, and every Raft group, so remember we break this data up into thousands of chunks, so the entire database is broken up into thousands of different Raft groups. Each Raft group has its own logical Raft log. So there is no one global log.
Right.
Each Raft group has its own log that is stored on that node.
So what I understand is that there's these different spans. So if you let's say you were storing every musician in history and you had this alphabetical store of all the different musicians, and it's the musician's name, their age, their discography, and this database was so big that you had to break it up into multiple sections. You've got A through F, you've got G through N, and so O through Z. You've got these 3 different sections, and you break these up into spans. So you have each of these spans, these entry spans, and this is I think you would describe this as sharding, and then you replicate each of those shards. And sometimes there's shard 1 and 2 will be stored on the same node, and then you have another node that stores shard 2 and 3. So if I have a node that's subscribed to shard 1 and 2, is there a single Raft log that has all of the transactions associated with shards 1 and 2, or is it separate Raft logs for each of those shards? Does that question make sense?
Yeah, it's actually kind of blurred in the real implementation. I mean, at the logical level, they are their own Raft logs, but given that a single machine could have tens of thousands of these shards on them, it would be impractical to have a separate actual file on disk for each one.
Right.
So logically, each one is separate, but we actually store the Raft logs in RocksDB as well, because RocksDB can gracefully coalesce these different Raft logs into the same files on disk for us. But then when we're reading them back out, we'll read them back out at the per shard level, and we don't ever need to read them out together.
Read them out at the per shard level.
So we'll read shard A through F's Raft log out independently of shard G through N when we read them back out and use them for anything, even if they are stored intermingled in this same RocksDB database.
Oh, okay. So you store them, but you have them you store them in the same file, but they're segregated in different places in the same file, so you can just read them in a linear fashion. You don't have all the reads intermingled.
Correct. Yeah.
Okay. Interesting. Okay. So we've talked about some of the sharding and the replication stuff. We kind of get it. There's a Raft protocol that manages the different sharding and replication layers, different sharding and replication nodes. Eventually we'll get to scale and talk about failures and stuff, assuming we have some time. But on top of this replication and distribution layers, you've got a transactional key value store layer. And before we talk about that, Let's define the term database transaction. Can you just explain what a database transaction is and then motivate the discussion of the transactional key value store layer that's on top of this replication and distribution layers?
Yeah, a transaction in a database is effectively a group of work that you want to do all at once. So it could be a group of writes, it could be a combination of reads and writes. But you want this to all be grouped up into one single entity that either all completes or all doesn't. And that's why in any database that offers transactions, those transactions are typically what's known as atomic. So they either every operation in the transaction finishes or every operation fails. And so transactions in any SQL database are considered ACID transactions, which is a very common acronym for atomic, consistent, isolated, and durable, which are really just properties of these transactions and how they interact with each other. But the core definition of a transaction is an atomic set of operations that are done together on a database.
Which might often be like, if you separated those two transactions, no problem. Or you separate those two operations, no problem. Like, go to the store, buy some milk. Those two things separately may not be, there's not much ambiguity, but if you say go to the store and buy some milk, there's perhaps more room for ambiguity. That's probably not a great example, but people who don't know what a database transaction is and why there is complexity associated with it, go look it up, I guess. Would you say that is that right? Or do you have maybe a better example that defines the transaction and the complexities that can result of a database transaction?
Well, I mean, the canonical simple example is if you have two bank accounts and you want to transfer some money from one to another,
right? You
need to take money from one and add it to the other. If you do these operations within a transaction, you know that either the money will be transferred or it won't. But if you do these as individual operations, you might take the money out of person A's account, but then fail to put the money into person B's account if something happens in between them, and then you're just taking money away from people.
Right. So transactions are something that you would want to synchronize. You want these two things to happen all at once or nothing. Is that?
Yeah, precisely.
Okay, great. So transactional key value store layer. What's going on there? Why do we want that?
Well, the Raft consensus algorithm that I was talking about earlier gives us consistency and atomicity and durability and all of this, but only on writes that take place within that one shard, because the shards aren't communicating with each other. And so in a SQL database, to be a SQL database, we have to support operations that touch all the data in the system at once. And not all the data in the system will not always be in a single shard. In fact, it almost never will be. So in order to support transactions across the entire database of a user, we have to have some sort of higher level mechanism on top of Raft in order to make those transactions atomic.
Okay. So what happens specifically at the transactional key value layer of CockroachDB? What's going on there?
Well, when a transaction comes in, we need some way of tracking the status of that transaction. And so when a transaction starts, we create what we call a transaction record for it. And that record just gives it some ID, has a timestamp for the transaction, and defines what status it's in. So whether it's pending, in progress, whether it's been completed, or whether it's been aborted. And that allows any consumer of that transaction to be able to tell what's going on with it. And as the transaction continues, any writes that happen within that transaction get associated with that transaction record. So if you start a transaction and write the key A, that write that you did will still be associated with that transaction, so that reads won't start reading it until that transaction's been committed. Because that would be a violation of isolation within the database if you ended up not committing that transaction later. So you can do a bunch of work, and then when you're done doing all that work, whether it's been a bunch of writes or a bunch of reads, you come back and you flip that transaction record to indicate that the commit is done. And at this point, all of the things that were written are considered committed as well, and reads will start having to return them. Okay.
On top of the key value layer, we finally get to SQL. We all know what SQL is. Now I'm forgetting. Structured query language? What is it?
I believe it's structured query language.
Structured query language, right. Take us through what happens on a query throughout the stack. So we all know why we want SQL, right? Like if you want, okay, let's say you're in Postgres, you're using a Postgres database, and you decide, I want to go to CockroachDB because I've heard about it's like ability to survive, all kinds of catastrophes and stuff, which we haven't even really gotten into. But I've heard about all these useful things, but I've got all these queries in Postgres. Well, we're compliant. CockroachDB is compliant with PostgreSQL. It's just the same query language. It's just doing different things under the covers. So, but with CockroachDB, you need to be able to implement that SQL interface. So we all know what SQL is. Take us through what happens on a query through these different layers that we've discussed. You've got SQL, key value, transactional key value store, replication and distribution, like the lowest level on disk. Maybe you could just map out, you don't have to dictate the entire code base to me, but just give me a description of what goes on in a query.
Well, when a SQL query comes in, we're essentially just mapping it to a series of key value operations. And so a query comes into us typically as plain text. And so we have to parse that text into a more structured query. We can do some semantic analysis of that query in order to optimize it and pick out what's known as an execution plan. So we take that text and turn it into some sort of execution plan, which is just a series of key value operations on the database. And so every logical row in a SQL table gets mapped down to one or more key value pairs. And so for say you want to do just a scan of your entire table, we'll take that query, parse it, turn it into an execution plan that just does a key value scan over the entire key range for that table and returns all the data back. And so there's just this layer that knows how to use our key value interface and to do the writes and reads required by SQL, and then map those key value pairs into the more logical SQL rows that are then returned to the user. So if you know how the underlying KV store works, then the only thing you need to know to understand the SQL database is just how you can map SQL operations to key value operations.
Okay, fair enough. So you have this database where the data is distributed and replicated, and you want to maintain consistency. So maybe I'm mistaken about this, but I think that intuitively it feels like there might be more network overhead in this kind of database when you need to, every time there's a read or a write, you want to kind of make sure everything is going on, everything is consistent. Again, I'm probably not phrasing this as well as I could, but is network overhead an issue? Is that something that you need to minimize during a database lookup or a write, and is that complicated?
So for any given query, the CockroachDB process that receives the query becomes what we call the gateway node for that query. So that's the node that's going to issue the most of the key value operations for that query. So if you do this naively, there is definitely a network overhead to it. So the simplest way that you can implement SQL on top of a key value database like this, which is what we did initially, is to have the node that receives the SQL query go ask for all the data to be sent to it. So it has to go reach out to all of the different nodes in the cluster that have the relevant key value data and read it all back before doing any operations on it. So this is the V1 of a SQL database on a distributed system. The V2, or the advancement of that, is to start pushing down as many operations as possible to where the data lives. And that's what we've been working on for the last year or so, where any part of a SQL query that can be executed closer to the data, we're moving closer to the data. So that means we're sorting data closer to where it lives, we're doing filtering closer to where it lives, we're grouping things and aggregating them closer to where they live, and then moving, running these things in such a way as to minimize the network traffic so that we only send back the data that really needs to be sent back. And that's just one way. I mean, there is, as you said, a lot of work that needs to go into minimizing the network traffic in any distributed system that's handling a lot of data like this. I don't know that the consistency aspect adds a whole lot of it, though.
Okay.
A NoSQL system still has to send all the data to all the machines for any given write. It just isn't happening right away, and still needs to have that level of background replication during operation to ensure things are in sync. So the actual quantity of data crossing the network does not fundamentally have to differ.
But in a NoSQL database, it might be more of a lazy, opportunistic consistency resolution thing. Would that be accurate?
Yeah, I mean, yeah, network congestion or delays wouldn't slow down your queries as directly as in a system where the communication is required.
Okay, cool.
It's also the case that NoSQL systems typically don't offer large analytic queries that need to move a lot of data around on reads, whereas a SQL system exposes an interface that makes it easy to read your entire database if you aren't careful about what you're doing. And so a SQL system is inherently going to have to be moving more data around on reads as a result, just because it offers functionality for reading and processing more data in given query.
Cool. Okay, so let's zoom out a little bit. When a database grows, there is something that needs to happen called rebalancing. And if we're talking about this database of musicians, and we've got musicians A through F, we've got G through N, we've got O through Z, and they're sharded some number of times. Let's say they're sharded 3 times, they're broken up into 3 shards, and you need to replicate each of those shards so that you've got some fault tolerance there. But if your list of musicians grows, like if it grows, by a large order of magnitude, then you're going to need to break it up into smaller spans. Like maybe now you need to break it up into A through D and E through J and so on. Just like, let's say you need to break it up into four different shards instead of 3 different shards. So a rebalancing needs to happen. What goes on during a rebalancing operation?
Yeah, so again, this is an area where you can do something simple, and then you can over time iterate on it to make it more and more sophisticated to handle more and more workloads better. So the basics here is that whenever a given range gets too large, say it has more data than we're comfortable with having in one of these shards, we have to periodically check and see how much data is in each shard and decide if it's too big, we're going to split that in 2. So that can happen locally. We don't have to go do much external communication for this. We can just say this shard is too big. I'm going to split it into somewhere in the middle. And now I have 2 shards, as you were mentioning in your example of going from 3 to 4. But then once you have that extra shard, you might want to move it around the cluster. And so we have a separate subsystem that is periodically examining the balance of data amongst all of the nodes in the cluster. And this subsystem has to know things such as how many shards are on each node and how much of the disk is used on each node in order to ensure we have a proper balance. And so it'll periodically examine these things and say, nodes 1, 2, and 3 have 50 of these shards each. Node 4 only has 20. Obviously, that's a bad balance because node 4 has far less than the average amount of data for the cluster. And so it's going to say, okay, we're going to add a replica for one of these shards onto node 4, and then remove a replica of one of those shards from one of the first 3 nodes. And this is just constantly happening in the background, trying to drive all the nodes towards having somewhere around an average amount of data. But that's the basic version. We're starting now to get more advanced and do this based on load as well. So you can imagine a situation where one of these shards has a very large amount of load on it. Say it has a bunch of hotspots based on the user workload. And you could get better throughput in the system if you broke that shard up into pieces and moved those pieces onto different machines so that you weren't overloading the machines that it was on. And so we're working now on splitting up these ranges, not just based on size, but also based on the workload that's coming in, and rebalancing them around the cluster as well, based on how much traffic each of these ranges is serving, so that we can kind of balance out not just how much data each node has, but also how many queries it's processing.
Mm-hmm. Okay, as we're drawing close to the end of our time, I would love to know, what are the hardest problems that you've had to solve or that you are in the midst of solving while you're building this cloud-native database?
Well, there are a lot of problems that we're trying to work on here, but I mean, the biggest one was really just productionizing this Raft protocol, this consensus algorithm, and making it work when all sorts of things can go wrong, and also when we're running so many of them. So we collaborate with the etcd database on our Raft implementation. And etcd puts the entire database into a single Raft group, whereas we're running thousands or tens of thousands or even more Raft groups. And it's hard enough to do just one, but trying to run so many of them has added even more correctness concerns, performance concerns, and scalability concerns. And so really probably the fundamental biggest problem that we've worked on over the last couple of years is just productionizing consensus and scaling it to this point.
And testing it, I imagine.
Yes, absolutely.
Okay. Google came out with their Cloud Spanner product, which is their productionized cloud service version of CockroachDB. Or sorry, not of CockroachDB, of Spanner, which CockroachDB is heavily influenced by. Now, I know this is not it's not a direct competitor, and the reason I know, it's in some sense a competitor, but the reason I know it's not like oh my god, this ruins our business type of competitors, because I remember when I was talking to Ben in our interview about CockroachDB, I asked him about this, and this was before Cloud Spanner came out, and it just seemed like he was not really concerned that this was going to be like a big deal. And I don't completely understand why that's the case, but I'm willing to believe it. Can you explain how you compete with Google Cloud Spanner in your own eyes, or how it's maybe a totally different product and this is just a bigger space than I realize, and what's going on there? Why are you guys able to kind of maintain such confidence in the face of a cloud service that in some sense originated this idea?
Yeah, Spanner was certainly the inspiration for CockroachDB, or at least the forerunner for CockroachDB. But there are a couple differences that make them, while they are competitors in some sense, they're not cutthroat competitors fighting to the end or anything like that. Cloud Spanner is fundamentally limited by the fact that it is a cloud service on Google's cloud platform. So it will only work for you if you're willing to run your workloads on Google's cloud, which already eliminates a very large number of potential database users, right? The world does not currently run on Google's cloud platform. And even though they may eventually, hope that is the case, it won't be for a very long time. And so Google's Cloud Spanner is already limited to people running there. Also, it only works for people who have truly bought in to running on Google's cloud as well. For any hybrid users who are partially on Google's cloud and partially elsewhere, they will need some sort of database solution for their elsewhere, whether that's their own data centers or another cloud. So even from the start, we're not, it's not like if Google Cloud Spanner succeeds, that CockroachDB will have no users. But there are also more subtle differences in what they support. So Cloud Spanner, or Spanner in general, was built within Google, which has a very different development environment from most other companies out there. And so Spanner doesn't support SQL in quite the same way that you might expect. So Spanner only supports SQL for reads. You cannot use SQL to actually modify the data in your database. You have to use a custom API to do so. And that might change eventually, but for at least the foreseeable future, any app that currently uses a SQL database will need to modify itself or be modified in order to use Spanner as its backend, because that's the only way that you'll be able to do writes. The last big difference between the systems is some subtlety around how transactions work. So when you're doing a write within a transaction in a typical SQL database, if you then do a read within that same transaction, you will read back the data that you just wrote. So if I write a couple keys and then do a scan over the entire table in a SQL transaction, in most databases I would read back those couple keys that I wrote. But in Spanner, you don't read back your own writes until after your transaction has committed, which is another subtle difference that will break a bunch of existing applications that might want to just port over directly.
Oh, okay.
So there are some differences between the two systems. Spanner has obviously been run within Google for years, so it's a very, very solid system, very reliable, and they have a great SLA on their hosted service. But there are some reasons that people can't go directly to it.
Understood. No, that explanation makes a whole lot of sense, and I look forward to reporting on this space more. It's very interesting. It's sometimes hard for me to delve into it the level I wish I could, because some of the lower level intricacies are still things that I don't quite get, but I feel like I'm making progress, and I think the listeners probably feel that way too. So, Alex, thanks for coming on the show. I really appreciated talking to you. It was a real pleasure.
Thanks. It's good to be here.
All right, cool. Spring Framework gives developers an environment for building cloud-native projects. On December 4th through 7th, Spring One Platform is coming to San Francisco. Spring One Platform is a conference where developers congregate to explore the latest technologies in the Spring ecosystem and beyond. Speakers at Spring One platform include Eric Brewer, who created the CAP theorem, Vaughn Vernon, who writes extensively about domain-driven design, and many thought leaders in the Spring ecosystem. Spring One platform is the premier conference for those who build, deploy, and run cloud-native software. Software Engineering Daily listeners can sign up with the discount code SEDaily100 and receive $100 off of a Spring One platform conference pass, while also supporting Software Engineering Daily. I will also be at Spring One reporting on developments in the cloud-native ecosystem. I would love to see you there and have a discussion with you. Join me December 4th through 7th at the Spring One Platform Conference and use discount code SEDaily100 for $100 off of your conference pass. That's SEDaily100, all one word, for the promo code. Thanks to Pivotal for organizing Spring One Platform and for sponsoring Software Engineering Daily.
Wow!